Hello, welcome to this session. Today, we're going to be talking about AI, artificial intelligence. This is going to be an introductory session. My name is Abhinanda, and my job will be to give you an idea of what AI is and what it does. We're going to talk about what is artificial intelligence. What do people understand by it? What it actually might be? We're going to talk a little bit about what goes inside an AI engineer's task. Primarily, the clever idea of neural networks and how they can solve AI problems. What are AI problems, you ask? Many kinds. But today, we'll be focusing on two very important AI problems, dealing with language and vision, how we hear and talk and how we see. That is what intelligence is about, is it not? So let's get going and begin talking about what do you mean by AI? What do you understand by AI? Do you think of, for example, robots? Do you think of machines in factories? Do you think of Google Maps? Do you think of some kind of voice recognition system? What does AI mean to you? For most people, AI usually refers to a set of tasks that sort of imitate what a human should do. Human intelligence is capable of doing certain things. Can a computer do those things? And when a computer appears to be doing those things, we call it AI. Intelligence shown by an artificial object, not a human being. And the point is that it is intelligent in the sense that this artificial object, let's call it a computer, can do things without being explicitly instructed in every case. Obviously, we'll have to give it instructions at some point. We'll do it using computer programs, but we don't have to keep giving it instructions all the time. In some sense, it learns. We'll see how it learns. That learning is a sign of intelligence. So, an AI system comes across as capable of thinking, of showing intelligence, and of translating that thought into action. For example, imagine a self-driving car. This car has to, shall we say, make decisions. Should I go faster, slower, change lanes, stop? What should I do? It has to act rationally and, in an ideal world, humanely, in a way that makes sense for other beings, humans, as well as possibly other AI systems. So what is AI? AI refers to a field of computing in which computers are programmed to perform tasks without being explicitly instructed that reflect tasks of thought and intelligence that humans routinely undertake. Now that's a mouthful, but let's see how it is executed. And right at the end, we're going to come back and close the loop and see whether you really believe that computer programs can do what humans can do. So, at the heart of artificial intelligence is this idea that there is a computer program that doesn't need to be told what to do all the time. In other words, it can learn. How it learns, the specific algorithms that go into learning, is a subfield of AI all on its own called machine learning. Today, we'll not go into the details of machine learning or the examples there. Suffices to say that machine learning provides in some way the architecture for which these programs can be sitting on. Now, machine learning has grown up forms. In other words, uses things like neural networks and deep learning, which we will talk about, because they provide the connection between machine learning and the tasks that AI is required to do. So therefore, what is the AI technology journey? It is to take machine learning algorithms make them sophisticated enough using things like neural networks and deep learning to solve problems in natural language processing and computer vision. This is the journey that I want to take you on. I'm not going to begin with machine learning. There are so many things to talk about in machine learning. But let me talk about neural networks, which is the special part of machine learning that really connects it to AI. What are neural networks? Let's begin with the computer version of it, the artificial neural network, which essentially states that if I take inputs and I pass them through an algorithm, I will get outputs, which is what any computer program essentially does. So the cleverness arises in saying that what is this hidden algorithm? What is in this hidden layer that takes the input and gives the output? The input, as we'll see, can be words, images, other kinds of data. And the output can be some kind of label associated with the words or images, or some translation or some feature. But this is a network in the sense that you can see inputs and various things that are hidden between the input and the output. But what's neural about it? That sounds vaguely biological. And in fact, the origins of neural networks do come from biology. How do we understand what we, for example, feel or see? You are seeing my picture on your screen. You are hearing words that I have said that have been recorded and are now being played back to you. How do you process that in your brain? How do you understand the words that you are hearing? So the signals come from your eyes and from your ears, and they go to your brain. These signals are processed by cells. We'll call them neurons. These cells, when they receive the information, pass it along these fibers or these parts of the cell that we can call the axon, and they trigger an electrical impulse. This electrical impulse is something that is not always triggered, and it is only triggered when the neuron kind of sees a specific kind of input that it understands. And then it, shall we say, fires. And when it fires, it passes the signal along. So what is a neuron? It's a specific kind of cell in your brain that takes a certain impulse, a certain signal, usually in the form of a small amount of electricity, and then processes it and then sends it along. It fires or it doesn't send it along. In a simplest case, you can think of it as the neuron fired or it did not fire. But that's one neuron. That's one neuron. The brain has many of these neurons. And so when the words come into your brain, so to speak, the words that I'm saying, they trigger many neurons. And these neurons in turn trigger other neurons. And finally, it goes to the interior of your brain and you say, oh, he said the word brain. And I know what the word brain means. Cognition occurs through this cascade of flowing information. This is the idea that an artificial neuron also tries to convey by saying that let me get all these different pieces of information, these various inputs, and let me put them into a neural network which consists of things that will fire or they will not fire. And when they fire, they will pass on the message to the next neuron, maybe as a 0 or a 1, or maybe as a number. And so therefore, there is this flow of information from the input to the output to a series of neurons, in this case, artificial neurons, which are basically rules that say, what will I pass if I get this input into it? And at the end, this will generate the output. And every time you do a calculation, and sometimes these calculations are very simple. You just sort of add things up, multiply them, and see what happens. So the brain may combine with different complicated chemistries. So the brain is essentially looking at things in chemistry and electricity. Electrons flowing small distances are chemistry. Electrons flowing large distances or larger distances are electricity. But artificial neural networks aren't that complicated. They're simply combinations of multiplications and additions cleverly done. But here's what makes it possible to do complicated things. You don't do this once. You don't do this twice. You have many, many layers. You have what is called a deep neural network. What is a deep neural network? It's got lots and lots of these artificial neurons. Each of these neurons takes a signal, processes it, and fires something out. And when it fires, it goes to another set of neurons that takes its input from the previous layer, and so on. And it keeps going until you get an understanding, an output, a classification, a prediction, a label, an understanding of a word, a recognition of a picture. And what will be the inputs? The inputs, as we'll see, may be phonemes coming out of someone's mouth, fragments of words, sound. They could be pixels in an image. They could be signals in, let's say, a medical signal, an ECG signal. They could be many things. But a deep neural network is this kind of mathematical object. These networks make AI possible. So AI is built out of deep neural networks, which are combinations, complicated combinations of simple neural units, which are nothing but things that take various inputs and throw out an output. It's their combination that makes it work. We'll give some small examples later. I should say at this point that not all deep neural networks look like this. Some of them look like very long networks in which words, shall we say, come one after the other, because the sequence of the word matters. These are sometimes called recurrent neural networks. Something is recurring, happens over and again, and needs to be remembered. There'll be other kinds of deep neural networks that we will see. So this is the machinery that goes behind modern AI. This machinery now takes different kinds of inputs. We talked about natural language processing. Let's begin there. Natural language processing is the ability of computers to process language that humans speak, natural, not computer languages, not C++ or Java or Python, but languages like English or Hindi, languages that have their own grammar, their own intonation, their own way of speaking and writing. And that grammar, that way of speaking and writing is called linguistics. Linguistics, therefore, needs to be a part of natural language processing. And the structures that these languages comprise of need to be made into computational structures and therefore computational linguistics. So computational linguistics is nothing but the ability to understand words. It is often thought of as a precursor to AI in the sense it's a way in which words are processed by computers before they can go into an AI system. For example, taking a sentence apart. But to make a computer understand that, it has to some extent understand what humans mean by words. And we don't always mean simple things by words. Our sentences may mean different things but look exactly the same. For example, somebody may say, I went to the bank. What does that mean? Bank as in financial institution, maybe to withdraw money, or bank as in bank of a river, maybe to enjoy the view. Or he made her duck. Does that mean that he made her head go down, as in maybe they were playing cricket? Does make mean make, shall we say, a paper duck? Or does made refer to cooking? The same sentence can mean different things within context. So computer, or the neurons of a computer, or the neurons of this artificial intelligence system can look at a sentence and be confused, just like the blind man and the elephant. What is this sentence trying to say? What does an elephant look like? Does it look like a rope? Is it smooth or is it rough? So similarly, what does bank mean? Is it a place with money or is it next to the river? So computer has to understand that context. It is not as simple as just interpreting the words in a sentence, because the same set of words can mean different things depending on what the speaker means. This is the problem that natural language processing tries to solve. This is the problem that AI systems have to solve. Otherwise, they're not intelligent. If you, for example, say, he went to the bank, he then withdrew money. Now you know what bank means. He went to the bank. The river was very nice that day. Now you know what bank means. The computer has to understand that in similar ways. That is intelligence. Now, this intelligence by now, through deep learning algorithms, has become fairly sophisticated, as you may have noted. Let's say that you're using some kind of word processor. Let's say you're sending an email or you're writing a document, and you may see that the software often predicts what you might want to say. Let's say you type the word thank, and the computer may say you, because most of the time when people say thank, they follow it up with something like you. Not all the time, but the computer may say that given the number of people who say thank you, it's quite possible that when you say thank, you're going to say you. And this can be based on the amounts of data that have gone into the neural network of the AI system. Remember the inputs and the outputs? And so therefore, these machine learning algorithms will suggest the right words. They might even suggest the right tone, the right way you can speak. Today, computers can generate text that show emotion, that show tone, that show contexts of various kinds. And they can be professional and they can be personal. But the point is to say that I will write or I will create words in a way that resembles what humans do. Alan Turing, one of the founders of computer science, proposed a Turing test many years ago, that when you talk to a person, can you identify whether the person is a human or a computer? And when this identification becomes difficult, the computer who's doing the talking can be said to pass the Turing test. Translation systems also do this. For example, they can say, I'm going to take a text in English and a text in Hindi, and then I'm going to compare them. I'm going to take lots of text in English, lots of text in Hindi, and if you tell them that they're saying the same thing, I'll try to match the words in the sentences, even though the grammar of the two languages may not be the same. The two languages may have the same message, but said differently. But if you give it enough text, a large enough corpus in the language of NLP, then it can find the language model and it can do translation. And these translation systems are getting better and better as the weeks and even the days go by. And more languages are being translated. All this because of the ability of a computer to handle large amounts of data and give simple predictions. Like, for example, what is the next word you might be interested in writing down? There are other applications that you might have seen. For example, a chatbot. If you go to a website these days, you'll see a little box that emerges on the bottom right, say, and it says, hello, I am so-and-so. Can I help you today? And maybe you type something in and it will give a response, much like a human. But it's probably not a human. It's a computer that has been trained through an AI system to say, if I get this word, then this would be an appropriate response. And at some point, it might even say, okay, I'm going to pass this message on to a human. Call centers often do the same thing, beginning with computer-assisted feedback. Another application is sentiment analysis. Sentiment analysis tells the user of the tool whether an amount of text, whether it is written or spoken, is conveying a positive sentiment or a negative sentiment. Is the person happy or sad? This movie is good is a positive sentiment. This movie is bad is a negative sentiment. But what about the sentence, this movie is good, not bad at all? That is also a positive sentiment. but it has the word good and bad in it. It also has the word not in it. Combining them in clever ways is what a computer's job is. Remember these recurrent neural networks I talked about? Words in sequence. So good, not bad. Good, positive. Not bad is positive in the sense that the not is cancelling the bad. And so this is a sentence conveying positive sentiment. And so therefore, this kind of application has made natural language processing commercially a very viable product. Because as you can see, given the amount of natural language data that is out there, all the social media information, all emails, chats, communications that a company may receive, if they can be parsed and people can find, are people happy with my product? Are people getting happier or are they losing faith in my product? That's a very valuable piece of marketing information. Similarly, chatbots allow a personalized interactive experience by having a smaller number of humans at the back end. Oops. Perhaps it's a problem because it means that you need fewer people to do the job. But isn't that what people worry about in AI? Humans being taken out of the picture. So is a chatbot a good thing? I'll leave that question for another day. But I want to leave you with the thought right now that AI systems are ethically complicated. They do in some way jobs that humans can do. And that has implications. Implications on ethics, implications on jobs, on tasks and responsibility and accountability. And that's a serious side of AI that we don't always talk about. But I just wanted to mention it as a context since we're talking about AI and it is really an important part of the discussion around AI. Remember, I talked about natural language processing and computer vision as two of the important tasks of an AI system. Let's now talk about computer vision. How can a computer see? How can a computer understand an image? Understand, shall we say, reality? What is reality to a computer as it sees it? Does a computer see the way we do? In other words, is the task of processing digital photographs the same as the task of us looking at the photograph? What about videos, which are essentially continuous versions of photographs? And so therefore, what does it take for a computer to look at things and understand in a way that we recognize as understanding? To understand and process vision. Now, when we talk about vision, there are so many different things that a computer can be asked to do if it can see things. For example, it can be asked to classify, what am I seeing? Is it a cat? Is it a dog? Is it a cow in the distance? What is it that I'm seeing? Maybe the task is not to say what it is, but is it there? Is there a person in this picture? This room should not have a human in it at this time. So if there's a person in this picture, then there is an intruder. Can it detect something in an image? But to detect something in an image, it needs to solve another problem, which is to say that inside an image, there is a person. Now that person is a part of the image. And to identify the person in the image, I need to form a segment. So what is a segment? A segment is a part of an image, maybe representing a person. So it has to be able to do segmentation that separates an object from the image, so to speak, and does it using the things that go into that image. And these are called pixels, the individual, shall we say, dots in the image. They could be black and white, they could be color. Of course, once I have objects, I can compare them. And therefore, I can compare even images to say, are these alike? Are these similar? Remember, I talked about the security application? So let's say I'm continuously taking a video. And intruder detection can be done by saying, oh, this image and this image, which are taken 5 minutes apart, are not the same. They are different. Something has changed in this room. Something is dissimilar in the room. This dissimilarity I will note and I will say, oh, something has changed. Flag up. So similarity between images, or maybe images that are similar are classified together. These are all images of, shall we say, clothing. These are all images of shirts. These are all images of pants. So, and all shirts are similar to each other in some clever ways. Pants are similarly similar, but they're dissimilar from each other, shirts and pants are. So similarity learning is about recognizing when things are close in an image sense and when things are far in an image sense. Once I've done that, I can also describe what an image is. I can say this image, together with its segmentation and identification with a larger set of similar images, should be given a caption. It should be said, this is this. Right? This is a picture of a neural network. This is a picture of a dog. That's a caption. Now, this caption needs to be also understood by humans, which means that the words have to go through an NLP kind of system. Cool, isn't it? It's like saying, I give a picture of a dog, and the computer automatically says, this is a dog. So from the image, it understands the dog, and then it can describe the dog using, shall we say, a form of NLP that I understand. It's vision and language in the same application. This is increasingly happening. You can generate images based on other images. You can generate cartoon forms of pictures. You can generate a cartoon picture of my face. You can generate images. This can be tricky because you can also generate fake images, so-called deep fakes. And that's not so nice. Remember this ethical issue of AI I was talking about? Here it comes again. Deep fakes can make people appear to be engaged in tasks or do things in an image that are not something that are real or natural. And that is a consequence of image processing that has good applications, but the technology doesn't itself have a morality. And perhaps some of the applications are not so good. I talked about video analytics, which is the idea of looking at video as separate images, frames, so to speak, and being able to detect changes in it, or being able to compress it in ways, sample from it, various kinds of things that you can do in video analytics. You might be doing some video analytics with this video that you are watching, taking certain parts of it out and seeing it again, etc., or querying it in some ways. Computer vision goes into the details of the image, of course, in different ways. And that can become tricky and complicated. Let's take a look at one particular problem in a little more detail, the problem of image classification. More precisely, I should say, object classification inside an image after segmentation is done. But let's leave the semantics out for now. Here is an image. I want to classify this image. I want to know what is it an image of. What might I do with it? Remember deep learning. The input is all the pixels in the image, all the little colored squares that you see, green and orange and black and white, etc. This is the raw data. So the first thing that it does is that it goes into something called a convolution layer, the first layer of the deep neural network. The convolution layer does certain very interesting things. It looks at parts of the image and it sort of adds and subtracts in order to find interesting features. For example, in doing additions and subtractions, it may be able to find edges. It may be able to say, oh, there is a difference between the right side of this particular feature and the left side. That means there is an edge somewhere in between. It will find features like that. These are sometimes called overall features or non-detailed features. So now, once I've found these features, the problem arises that if these features can be found in all parts of the image, there are so many things I can find. The number of features blows up because all parts of the image seem to have interesting pieces of information, interesting color changes, interesting shapes, interesting textures. Texture in an image is nothing but color changing rapidly. So now I've got too many features. So now the next layer of the neural network is something called pooling. And what pooling does is it somehow subsamples or reduces the number of features. It says, let me take some of those features, sample from the features. Let me take the maximum or the most important feature. Let me take an average of the features. Many ways in which I can pool or combine features, brings it down. And then this is the magic. This trick of expanding the image by finding many features and then pooling the features into something manageable is repeated over and over again. Not 3 times as you see here, but many, many times. And every time you do this, you find features based on features and then pooled and features based on features. And so this feature set is created that is able to distinguish between things. And then if you tell the image that, oh, this is a cat, now it will be able to associate this final set of features that it has come up with a cat. And because it has so many images to look at, it has so many kinds of features that it can associate with a cat. It can say, oh, with a cat, I will associate these particular features, and that is that root in the neural network that somehow seem to be fired. That is the root of the neural network that gets fired by the cat. Many roots maybe, but different roots get fired by different labels. And so now when a new image comes in, I can then say, what root is this image firing? And I'll say, oh, that looks like the route that a cat takes through my deep neural networks. And I will identify it as a cat. But maybe I'm not sure. Maybe I'm only 80% sure. Maybe that there are some dogs that also look like this. Maybe young dogs, maybe a puppy also looks like this. So maybe puppies and kittens are harder to tell apart. I don't know. If you have them, you probably know. But there may be some doubt in the algorithm. There's an 80% sure it's a cat and 10% sure it's a dog, and some small probabilities or chances that it's something else. But each of these animals will have a particular set of roots of features and things firing on and off, or weights, as machine learning people call them, that are associated with the label. And so what neural networks do is create these pathways. And these pathways allow it to classify and classify very well. And because the network is deep and the convolutions pick up interesting features, this works surprisingly well. Other possible applications: facial recognition. Facial recognition works how? Simple. First, identify the face, segmentation. Second, within the face, identify certain features. Let's say the eyes. Let's say the mouth, let's say the nose. Identify certain features that combine these. For example, distances. Distances between the eyes and the nose, distance between the nose and the mouth, between the eyes, length of the nose, etc. The proportions of the face. These are all features. These features can now be extracted again through clever combinations, perhaps clever combinations of convolution pooling as well, into saying, oh, this particular set of features corresponds to this person, this lady. And so if this is the picture I see, this is, say, Anne. And so therefore I'll be able to identify the face with the name and therefore recognize based on the same kind of feature understanding. More complicated. What about pictures with many, many possible things in it? And what about moving pictures like videos? Again, let's break apart the problem. Video, nothing but many images. Within each image, segmentation tells you what each of these, that there are several segments. Recognition tells you what each of those correspond to. Truck, car, road separator, signboard, etc. So, segmentation, recognition allow you to be able to say, this is what I'm looking at. And then again, the comparison across frames allows you to say, was it the same object that was moving? Is it the same truck in the next frame, in the next image? I might even do something very sophisticated and say, you know what? When a car is blocking this lane separator, I have a violation, and some light will go on saying some rule got violated. So I can impose rules on this and do analytics, which says, is something wrong? Or maybe it's a simpler problem. Why go that far? Maybe it's a simpler problem. Maybe it's just a problem of counting. How many cars crossed in the last hour? How many cars crossed? I recognize a car, I count it. And so computer vision can be put through a series of steps to, at the end, identify people and see whether traffic is flowing smoothly or not. All with some basic components of analytics, of features built on pixels that pass through convolutions and pooling type algorithms inside deep neural networks, much as we saw in natural language processing. Welcome to the world of AI. Welcome to neural networks, to the use of neural networks to things like natural language processing and computer vision. AI is nothing more than taking complicated data like words and pictures and signals, putting them through sophisticated algorithms and getting outputs that make sense to humans, like translation and recognition. That's all that AI is. I make it sound very simple, but there's detail. And that detail is what I hope you will spend some time in finding out, whether you do it online or through courses or simply by trying it out. But next time you see a chatbot, or next time you see a camera that sort of turns towards you, think of the algorithm that went behind it. Think of AI. See you out there. Somebody is seeing you out there. It's a camera. But this time, I want to see you out there. And I want to see you doing and learning AI.